Hey there! Today, we're going to talk about a super clever tool in digital electronics. It's something that takes a total mess of code and makes it simple. I mean, really simple. It's called the Karnaugh Map. Let's jump right in and see how this thing works.
When you think about it, everything in our digital world, computers, phones, you name it, it all comes down to ones and zeros. But that simple binary system, it can get messy fast. It can become a real jungle of logic. So the big question is, how do you cut through all that chaos and find the simple pattern hidden inside?
Okay, take a look at this thing on the screen. Yeah, that's a Boolean expression. It's basically the language of computer logic. Now, imagine trying to simplify this mess using just algebra. It's like trying to untangle a massive, knotted-up ball of Christmas lights. It's long, it's confusing, and if you make one tiny slip-up, the whole circuit it's describing could just fail.
And that right there is the big problem we're talking about. To design good, efficient circuits, you have to simplify these expressions. But doing it with algebra is just a huge headache. The good news? There is a much better way.
And this is where our hero, the Karnaugh Map, or K-Map for short, swoops in to save the day. See, instead of fighting with all that abstract algebra, the K-Map is visual. It's intuitive. It literally turns a gnarly calculation into a simple graphical puzzle.
So let's get a closer look at this solution. I don't want you to think of the K-Map as some scary, complicated chart. Think of it more like a special kind of puzzle board. It's designed to help you see the simple answer that's hiding in all that complicated logic. It really is the ultimate visual shortcut. Okay, so if we're going to get technical for a second, a Karnaugh map is a graphical method for simplifying those Boolean expressions. Its whole job, its entire reason for being, is to take something complex and shrink it down to its simplest, most efficient form. And that's absolutely critical for designing the logic circuits that make all our modern tech work.
All right, so how does this puzzle board actually work? Well, just like any good game, it's got a few simple rules. And once you get these rules down, you can pretty much solve any logic puzzle that comes your way. So let's go over them.
Okay, the real secret sauce here, the magic behind the K-Map, is something called gray code. What is that? It's just a special way of ordering the numbers so that only one single bit, a 1 or a 0, changes from one square to the next. Now, that might sound like a tiny detail, but trust me, that special ordering is what makes the whole thing work. It's what lets our brains spot the patterns visually. You'll see in a second. So here are the rules of the game. Super simple. First, we're looking to group up all the ones on the map. But there are a couple of catches. The groups have to be a power of 2 in size. So you can have groups of 2, 4, 8, and so on. And your goal is to make these groups as big as you possibly can. Oh, and here's a really cool trick. The map wraps around on itself. The top edge is connected to the bottom, and the left is connected to the right, kind of like in Pac-Man. As long as you make sure every single one is covered by at least one group, you're good to go. Okay, that's enough theory. Let's actually do this. We're going to put these rules to the test and watch the K-Map do its thing. This is where it all clicks. So we're going to simplify this function right here. Don't let the notation scare you. All this is saying is that our circuit is on or has a value of 1 at 4 specific spots, called minterms. In this case, at positions 1, 3, 5, and 7. So our mission is to put those ones on the map and see what pattern we can find. And here it is, our empty game board. This is a 3-variable K-map. See how variables A and B run down the side, defining the rows, and variable C is up top for the columns. Every single one of these little squares corresponds to one of those minterm positions, from 0 all the way to 7.
Okay, time to fill it in. We just put a 1 in the boxes for minterms 1, 3, 5, and 7. And everywhere else, we fill them in with zeros. And just like that, our puzzle board is all set up. Now we just have to solve it. And here it is. This is the aha moment. Remember the rule? Make the biggest group you can. And what do you see? All 4 of our ones line up perfectly in a single column. That's a group of 4. So what does that tell us? Well, look at the rows. As you go down that column, the values for A and B are changing, right? They're all different. But for every single one in that group, one thing stays exactly the same. So what does that mean for our final answer? It means that whole, ugly, complicated expression from the beginning, it all boils down to just this. F equals C. That's it. That is the incredible power of the K-Map.
We didn't have to touch the algebra, we just found a visual pattern and turned a huge problem into one single letter. How cool is that? Now, this whole technique isn't just for simple 3-variable problems. The same ideas, the same principles, they scale up to handle much more complex situations. And there are a few other cool tricks we can add to our toolkit. For example, sometimes there are input combinations that just will never happen in a real circuit. We can mark those spots with an X for don't care, and we can use them to help us make our groups even bigger, which is great. You can also group the zeros instead of the ones, which gives you a different but equivalent answer. And yeah, you can do maps with 4, 5, even 6 variables by hand, but for anything bigger than that, you're going to use software. But guess what? That software is using the exact same principles we just learned.
So let's get to the big question. Why does any of this actually matter, like outside of a textbook? Well, it's pretty straightforward. When you have a simpler expression, you need fewer physical parts, fewer logic gates to build the actual circuit. And fewer parts means the circuits in our phones, our computers, our cars, they can be faster, cheaper to make, and they use less power. This is literally the foundation of smart, efficient hardware design.
When you boil it all down, the Karnaugh map is just this beautiful example of how powerful visual thinking can be. It takes a problem that's abstract, that's easy to mess up, and it transforms it into an intuitive visual puzzle that anyone can solve. And that kind of leaves you with a final thought, right?